what the basic principles are. So typically what we see it in let's say pinhole cameras or in regular cameras that are flat, you're going to see a pyramid shape that provides basically that particular field of view that the camera and the lens can actually observe. So what ends up happening, if you look at it from the top or on the side there, you're going to have on the basically part of the bottom of the pyramid what we call the perspective center. That's where the center of the camera is located, or we predict that the center of that camera or the lens is located there. Then we're going to have the image plane. This is, of course, this is exaggerated. It's going to be much smaller or in that way. But this image plane is basically where you can see that particular image on top of that. So this is if you look at it from the top. And then the other one is the object space, whatever you see around it. Of course, I just draw this as a plane, let's say. It's not necessarily a plane. Sometimes it's going to have some sort of depth. But regardless, it's going to be projected onto a plane. This is what we call the projective geometry of the camera. There's going to be some sort of projective transformation of the object space onto a 2D image plane of the field of view of the object space that we have. And what is important here is that every point in the object space that would intersect this image plane at a particular point, which we call a pixel. That's where that pixel that we talked about would be. Meaning that regularly when it's taking this picture, it's going to discretize the regular object space. But when you back project it onto the point, we are going to see a point in the object space that represents this pixel. And what's important is that this is supposed to be a line, meaning that ideally, based on a completely calibrated and perfect camera, we're expecting the perspective center, the object point, the image pixel of a particular point, and its object space representation of that point all have to lie on the same line. This is what we call collinearity, which we're going to use this in order to calibrate it, meaning if we have object space and point represent and image pixel representations with respect to the perspective center that do not are not collinear, what that means is that that needs to be calibrated, meaning that our calibration needs to be with respect to enforcing collinearity between these 3 points, right? So this is basically how we can represent this. Now I'm going to go in a bit more detail about, okay, so we have this. How do we get the information that we want with respect to projective transformations? And how does this projective transformation work? And how is it relating to us with respect to various different aspects of photogrammetry? So let's talk about the basics for a simple pinhole model. So every point here is going to go back projected and represented by a pixel point, X and Y. And this is what that image plane was. Basically, we have the X and the Y direction here. We have the X and the Y direction, sorry, X and the Y direction of our image plane. That's basically where we call our principal axis. So this is what we call principal point. This is what we call principal axis. So here, if we basically look at this 3D objects from the side, we have this as our Y, and then we also have this as our Z. We basically look into what this point is going to be represented by in the image plane from the side here. So this is going to be the ZA, which is basically the coordinates of this system. And this is going to be the YA, which is the coordinate of this point in the direction of the Y. And this is, let's say that this is the representation of our image plane. This here is what we call focal length or principal distance. In photogrammetry literature, you're going to hear a lot about principal distance. In computer vision, you're going to this is typically referred to as focal length. as well. So we have this focal length, okay? We have the ZA, we have this YA. What we can do is we can get this information, right? This is a right angle triangle. This is the right angle triangle. These two are similar, right? So this here divided by this here, which is YA, is equal to F divided by ZA, or this would be equal to F divided by ZA times YA. So you can get this. Similarly, you can get how it's going to look from the Z-axis, which from between on the XZ plane. So from the top, when you look into that, basically you're going to have this F here, which is what we call the principal distance or the focal length. We're going to have the ZA, we're going to have the XA here, which is the point coordinates here. And by means of the similarity between these right angle triangles, we can get what the distance from the principal points would be in the X direction, for instance, here, and in this one in the Y direction here. Okay, so this time it would be F times XA divided by ZA. So let's formulate this. Essentially, if we have our XA in our image plane with respect to, let's say, a 0, 0 coordinates that we have. So we found out that from the principal point, we have F, Y, A, Z, A from this side and F, X, A, Z, A from the X side, right? So we just sum it up with our PX, which is going to be the pixel coordinates of our principal point, and py, which is the pixel coordinates of our principal point in the y, and the other one was in the x direction, right? If we want to represent this into a matrix format, we can easily do it through this. What this is what we call the K matrix. This K matrix is, and here basically what I've done is, this K matrix represents your interior orientation parameters for a simple pinhole model or a simple pinhole camera. We're going to talk about how we have also additional parameters for radial lens distortion as well, but assuming that there's no radial lens distortion, this is going to be your camera parameters that you need to calibrate for, meaning that we need to know the F, we need to know the PX, and we need to know the PY. And now, if we have a rotation and translation, this formulation would just change into this formulation. Let's talk about what it even means overall with respect to our multi-view geometry. Now we've understood that every point in space can be back projected onto the image plane. And from that, we would be able to extract the information that we want from that if we have the basic projective matrix of a particular camera. And that basic projective matrix was a function of what? Was a function of our interior orientation parameters, which were the focal length and the principal point. And also it was a function of our rotation and translation with respect to our origin coordinate system. Okay? This one is basically the same. You just have a R times R and T, which is the rotation, and a translation from that origin. So this time, our coordinate system looks more like this, where the X prime is the pixel coordinates of a point into this image plane. K prime is supposedly if these two are different cameras and have different interior orientation parameters, which again, I emphasize is a function of our principal point and our principal distance. If they're the same camera, we're expecting these two to be exactly the same. And then a representation of rotation and translation. Okay, so what is beautiful about this is that the two camera centers, with respect to this X, which is going to be the final points there, will represent a plane. So essentially, our camera centers that are projecting back the same points would have a plane created with respect to that particular point. Okay, so let's just look at it from a top position in these two. What ends up happening here is that this here represents a plane for us, because this is collinear, this is collinear. This X is the projection of this point in the object space onto our camera plane. X prime is in our pixel image again as well for the camera C prime. Now, if we project this back onto it, we're going to get this point. So what is this? The same way that we had this point being projected back onto our X prime, okay, that created that, projected back into camera C prime. If we have a particular camera position at a particular point, we project it back, we're going to get a point which is called E prime. This is what we call the epipolar point. How E prime is actually going to be identified is the same as this. If we want to get this projected into this, our X prime would be P prime times X, right? So the epipolar points would be also P prime times C, which is the coordinates of that. Now, what's interesting about this, because this is a plane, right? So X, C, and C prime are on the same plane. Essentially, how it would relate these two together is that we have this plane that intersects this other image plane, right? That creates what we call this epipolar line. This epipolar line represents this one thing, that a point that is X here could be represented by any point if we do not know the exact coordinates of this, but we know that this point X is here and we know the camera position here. This point X could be represented by any point on this line into image C prime or camera position C prime. That's, of course, we have the exact same phenomena happening on the other side. If we project C prime onto the other plane, what ends up happening is that we have E, and E is, of course, what? P times C prime, okay? That would give us the coordinates of the point here, which is called E in the image plane. Again, we have the same epipolar line that represents the intersection of this plane, okay, with the image plane in camera C. So let's see how we can actually quantify this and make this into a nice formulation so that we can actually get our orientation or relative orientation or some sort of relative projection between two images without having information about our X here. Guided matching comes back to this epipolar line. So just remember this as our point, meaning that typically with matching situations as well, we, instead of having, because we still want to match between these automatically, if we get a pixel point here and we have some sort of idea of where the geometry is, we can actually only search for similar pixels or similar correspondences on this line, which we call the epipolar line, right? Because no other correspondence of this could be on this, on anywhere else in this image but this line. Let's start with the basics. We talked about how X is equal to P times X, right? This is small x, which represents the pixel coordinates of an image. This is the large X, which represents the object space coordinates. This is a simple linear equation, and one of the answers to this is P plus X plus gamma C. C is the location of this. Gamma is basically an arbitrary scale factor for this particular formulation. And P plus is the pseudo-inverse matrix of P. Basically, because matrix P, if we go back to it, is going to be R and T, right? And times, of course, K, or in this case, I and 0 times K. And K was a 3 by 3 matrix. I is a 3 by 3 matrix. And then 0 is a 3 by 1 matrix, okay? So this in combination would give us a 3 by 4 matrix. Typically, if we want to do a simple, let's say, inverse, it would only work if we have a square matrix, right? Like, let's say, a 4 by 4 matrix or 3 by 3 matrix. This matrix P, which is our projective matrix, is a 3 by 4 matrix. So we have to create a a 4x4 matrix to be able to, or square matrix to be able to do an inverse. Now we have x prime equal to p prime times x. We basically plug in this formulation of x into this other formulation. What we're going to get is p prime times p plus x plus gamma p prime c is equal to our x prime. To make this shorter and nicer, we want to get rid of this. So we multiply this by the cross products of this particular vector. This vector times its cross is going to be 0, okay? So we basically multiply this by its cross. What we're going to get is this cross product of this and this. Now, what we want to do is we want to get rid of this x prime. So what we do is we basically multiply the two sides by x prime transpose, which that means that we have a cross product of a particular basically vector with another vector times its own vector. It would always be 0 as well. So this here, what we call a fundamental matrix. So here I've basically replaced the p prime c by e prime. Why? Because e prime is actually, which this is basically our epipolar point representing camera C. This is going to be c times p prime, right? So this is going to be exactly this, or p prime times c, right? So this is going to be the e prime vector there. And from that, we can get this, which we call the fundamental matrix. This fundamental matrix is a 3x3 matrix, so it has 9 elements, 8 of which are independent from each other. What this means is that if we have a particular set of point correspondences between two images, we would be able to estimate the F matrix, which is going to be our fundamental matrix, which this fundamental matrix is a representative of the epipolar geometry between the two views. Now, what's cool about this is that if we have some estimates of k and k prime, which we, again, I bring it here, k is our interior orientation parameter or our calibration matrix, however way, depends on whether it's computer vision or photogrammetry, it's known differently. This is representative of our focal length and our principal points, okay? If we have that ability, we can now decompose this outside of these two, right? We can just bring it out. And what we get is what we call the E matrix, okay? So what's interesting about this is that this E matrix is only related to our exterior orientation parameters, meaning our rotation and translation, meaning in a very arbitrary coordinate system, we can put the first camera coordinate system as I and 0, which is I is our identity for our rotation, and 0 is our translation with respect to a coordinate system. The second coordinate system, if we have identified the F and we've had identified the K, we can basically calculate the R and the T with respect to the information that we have only from the E matrix. Meaning, if we have calibrated cameras and we have some point correspondences between them, we can get the relative orientation parameters, that's a better word to describe it, meaning the rotation and translation between one camera and another camera view or another cam. This is basically the basics that we're going to use in order to extract the information that we want and then back project it onto reality in order to create 3D point clouds. So what the reality is that we need some sort of point correspondences. Typically, we have some computer vision applications to do that. Sometimes we can do it manually as well. The problem with manual in practical scenarios is that we now have to extract each and every one of these very manually. It's going to be quite tedious. Why? Because the calculation of the F matrix, the calculation of everything else is dependent upon how well distributed our points are. The automatic ways of extracting the features is actually nicer because now you have the opportunity to extract these automatically from, let's say, established methods like scale invariant feature transform, which we briefly talked about it in the first session as well. You basically have to magnify a particular image in multiple layers, and then you also add Gaussian noise and blurring to that, and you find points and pixel points that with all of these magnifications and with these changes in noise do not change in particular features that are unique to them. That's why it's called scale invariant as well. And from that, because you can find these points, now these points would be our feature points here. So these are our feature points. Then you have to do a matching between them, between how well these feature points are represented. Then you do a matching, so you can match it. Some of these points are not going to be accurate. For instance, if you take a look at here, this has been, if I'm not mistaken, matched with here. This is not correct, but the reason why it's matched there is because if you probably take a look at the geometry and the F matrix that is identified, this point and the actual correspondence of this, which is here, is going to be in the same epipolar line. So it has identified, for instance, this as the point that is similar, for instance, and sometimes you're going to see that. So this is what's very interesting here. So this and this here. And that's where, if you don't have more information from it, and if you have only two view information and you don't have accurate calibration parameters, you're not going to be able to get a proper, let's say, idea there through what we call the guided matching, which I discussed very briefly there. So now you have some features there that have been properly matched together, or to some accuracy they've been matched together. We need 7 of these to be able to determine this through some sort of manipulation, 8 to get the linear solution, and more than that to be able to have an overdetermined system, so that we can now say, okay, a particular point is its residuals are not as good, so we're going to remove that as outliers. And you can do that. So I've actually created some very fundamental methods in robust statistics in order to extract overall outliers from non-outlier points. So you can utilize that for any type of system of equations with least squares adjustment in a basically accurate way and a non-parametric way. But sometimes stuff like this would not be possible, and the reason why is because now this point is most likely on the epipolar line of that, which is not incorrect, meaning that through this, we cannot make that distinction whether that point is actually there or somewhere else on this line if we have no information regarding their object space correspondences. If we have the camera matrix, if we have the calibration matrices of these cameras or these views, if they're the same camera, these two Ks are going to be the same, right? If they're different cameras, they might be different. But in what we typically do with structure from motion, which is simple, we have like a smartphone camera or whatnot, we do a video, and then we decompose this video into images, and then we do the same task. So if we have a good estimation of our initial camera parameters, we can get the we can basically get the E matrix with only 5-point correspondences, and then we can get what we call the relative orientation parameters directly from that E matrix through singular value decomposition, which I'm going to explain very briefly later as well. So what this means is, if we don't have the camera parameters and we have only 2 views, we can recover the camera matrices up to a projective ambiguity, meaning that if you see a projective reconstruction, this projective reconstruction might have differences in terms of how it's skewed, how it is. It's not going to be the same as, let's say, a similar object that you basically scaled it or not scaled it. And this is where we call the projective geometry. So we can actually recover the scene given nothing else but our 7-point correspondences and our and basically the correspondences between them. We can calculate the F matrix, and from that we can estimate the P for the first one and the P prime for the second one. Well, M and E are actually, we can basically get it from E prime is basically, you can get it from here. You don't even need that. You remember that P prime stuff that we talked about. We don't need that there. We can actually get it directly from the fundamental matrix. This is the epipolar point. And M is basically the cross product of the epipolar points in matrix form times the fundamental matrix. If we have our nice K matrix there, here, we can basically get our E as basically our T and R. And basically from this, we can extract the T and R through singular value decomposition. And from that, we can get our P matrix and the P prime matrix because we have an estimation of the K. Actually, this needs another K here. Sorry, I apologize for this. This is just a typo. So I'm going to fix that. But this requires a K to be multiplied here. I've just missed that here. But what that means is now we can get the camera matrices properly, and we can get our rotation and translation properly as well between two different cameras. Okay. So now we have an idea, given our camera parameters, interior orientation and other types of parameters, and given our actual scene and some features, we would be able to extract what the relative position is between one camera and another camera, which is very important. Why? Because then we can back project these points onto our cameras, right? This is literally what we want. We want to know where our relative orientation between the two cameras is going to be, right? From C and C prime. Once we know where that relative orientation between the cameras is going to be, we would basically back project it towards the X, right? What this means is if we have an X prime here and an X here, that are the same corresponding points, if we know the relative orientation between the two cameras, we can triangulate it with respect to the same ray that we talked about is going to be in the same line, and this one is going to be in the same line. Wherever they intersect is going to be our X. So how do we do that? Basically, every ray that we have, if you S times that going forward, you're going to get some sort of something projecting it back. So this S represents our scale factor. How far do we want to go, or how far do we want to come back, right? And points from different cameras, of course, would have different scale factors. Actually, points in the same image would have different scale factors because we have different positions for particular points, right? What we have to do is we have to eliminate this S. And once we eliminate it and we write the P by means of P1, P2, and P3, which are the row matrices, row vectors of the P, this basically would be a 1/4 matrix. From that, if you do some calculations, we're going to, and some manipulation here, we're going to get to the simple equation, which is A times X, Y, Z, T equal to 0. Where basically A is represented by this. I'm not going to go through the calculations because it's quite actually simple. Once you do that and once you eliminate the S through the second term here, which you can easily do by expanding these two matrices and put where the S is equal to and then bringing it back, you're going to get this nice 4/4 matrix here, which this 4/4 matrix is now going to be the null vector for this 4/4 matrix is going to be your X, Y, Z, and T coordinates. And for us to be able to be consistent, what we typically have to do is we typically have to have the same T for everyone, right? This T would give us the factor, but it's going to be different for different what is it called, projections that we do and different triangulations that we do. So what we have to be mindful of once we do these types of calculations and once we get what that point is, we have to divide it by this t in order to bring it back to the xyz1 coordinates that we have. And we have to do it for all of these points in order for us to be able to show it all together. Otherwise, each of them would have a different t, and that different t would make that whole geometry skewed or incorrect.